Let's do it this way. So, thank you, Yoontae, for joining this guest lecture session. So, Dr. Yoontae Jung is my old friend, and he obtained all of his degrees from South Korea, KAIST, from bachelor, master, PhD, and he is now working at imec, Belgium, which is a Belgian institute in microelectronics, which is very, very nice institute. World-leading research is going on there. So Yoontae will talk about fundamentals and trends of neuro-recording ICs. So Yoontae, please go ahead.
Okay, thank you, Guante, for inviting, and thank you all the students for having me here. So today, I'm going to talk about fundamentals and trends of neuro-recording ICs. And my name is Yoontae Jung, and I work at imec, an electronic and photonics IC design team. Let me first briefly introduce about imec. And imec is a world-leading research and development institute in nanoelectronics and nanotechnology. And together with many industry and academic partners, we aim at impacting the society with innovative solutions and technologies. We have about 10 sites in worldwide and over 6,000 international R&D top talent from over 100 nationalities. And we have unique 3.5 billion worth leading edge semiconductor fabs. And in 2024, we achieved like 1 billion euro revenue from industry, regional government, and EU programs. And we have, as you can see in the lab, we have, of course, 200 millimeter fab, and also 300 millimeter fab is also ongoing for high process node, such as sub 10 nanometer CMOS process. This is imec is presented all around the world with offices in Belgium, UK, Netherlands, US, and the headquarters is located in Belgium, in Leuven, where I am currently working at. Let me briefly introduce about my education experiences. As Guante told you, I got my bachelor's, master's, and PhD degree from electrical engineering KAIST, South Korea. And starting from 2024 August, I've been working as a full-time researcher at imec Belgium. And I'm incoming assistant professor starting from next month at Aalto University, South Korea, planning to do some research related to biomedical sensor interface and process in memory works. For today, I'm going to briefly introduce the overview of neural interfaces and neural recording, followed by circuit designs for electrical neural recording. And of course, I want to highlight imec's high-density neural recording ICs and some state-of-the-art work of direct digitization neural recording, and it will be wrapped up by technology and outlook and challenges. For some remarks, some of the slides of imec technology are based on SSCSS lecture from our team leader, Carolina Moore Lopez, and our department director, Nick Van Helleputte. Let's think about what we have learned so far in this class and also from your previous courses related to circuit design and semiconductor. So for analog integrated circuits, you guys have already learned and did some cadence simulations and a lot of things about amplifiers such as this one, like voltage cascade, transfer function, second order system, and the analysis. And I checked that you guys also did some filters related to Butterworth or Chebyshev, that kind of filters. And of course, if you're an analog circuit designer, you have to be familiar with feedback systems. And for the rest of this course, Quanta told me you're gonna learn also data converters. And if you're planning to do deep dive in this field, you're also gonna learn about power management IC, RF wireless, wireline frequency synthesizer, which is pretty popular. So where are all these analog ICs are really used? Now we learn it and we have to know where these analog ICs are really applied to. And short answer is, of course, everywhere. You can check it in these displays that you're seeing, and of course, there's audios, and it's everywhere in your smartphone, laptops, And of course, nowadays, automotive is not just a vehicle, but it's one of, we can call this as one of the like large computers that has wheels. Of course, 5G, 6G communication, IoT, and nowadays hot field AI computing, AI inference chips, and physical AI and robots, and a lot of sensors related to it. And you may heard all of this from a lot media, social, and newses, but is there any other application that you're not that familiar with? So let's first go with this video. So is this is a demo from Neuralink that this monkey is doing ping pong, which they call as mind pong. That actually only uses this monkey's neurosignals to control this ping pong's interface. So actually, where you can see left here, this is the monkey's neurosignals, and monkey could control this ping pong only by using these neurosignals. He doesn't care about it, so he actually thinks he's moving this joystick, but this joystick is actually turned off. So this monkey could control all this mind pong only using the neural signals by using the Neuralink product that's implanted in the brain of the monkey. So this field is called as biomedical IC. So biomedical IC or biomedical integrated circuit design might be a field that you may not be that familiar with. And one of the biggest advantage of this area is that the analog ICs we design can provide direct and visible benefits to real people's lives. And this can be categorized in three big fields. And the first one is wearable device, where you can sense your ECG, SpO2, heart rate, and you might be really familiar with because some of you might have this Apple Watch, Garmin, or Galaxy Watch. And the second category would be implantable devices that really implant in human or animal's body, which is composed of neural interface, pacemaker, cochlear implant. And the last one is diagnostics and point of care, for example, as glucose monitoring, cell imaging, and drug delivery. And in this talk, I would concentrate on the neural interface. So what is neuro-recording? We all know that our brain is one of the most complex organs of the human body, and it is responsible for our cognitive, sensory, and motor functions. But there are many illnesses and diseases that affect these functions if the circuit of brain is misconnected, such as Alzheimer, brain tumor, ALS, and epilepsy. And this is why a lot of doctors and neuroscientists around the world are trying to investigate the biggest mysteries affecting the worldwide population. This neural interface has been developed over the years for several purposes, and one of that purpose is to try to understand how this brain works. Now, let me briefly introduce about electrical neuro-recording and neurosignals. These are neurons, and in our brain, we have about 100 billion neurons. And if one of these neurons spikes and provide this action potential, these electrical signals transfers through these axons. And at the terminal of these axons, there are synapses connecting this axon and the next neuron. And the information is transmitted by chemical reaction using neurotransmitter to the receptor. Therefore, if you want to decode what people think and what people intend to do, the easy way is to just probe these electrical signals with neurons and the axons. If you can check and sense and obtain the information from these neurons and synapses, we can decode what people really think. Brain implants such as the one shown here are being currently used for two purposes. First one is recording, to just record the electrical signals of the brain signals, which is widely used in neurosciences to understand the brain and understand this neuronal communication. Of course, it is nowadays largely used also in this brain-computer interfaces. The second purpose is the stimulation, which is to stimulate the brain's target area. This stimulation method is largely used to treat neurological disorders such as Parkinson's disease, epilepsy, by stimulating the target area with electrical or ultrasound stimulation. Of course, nowadays also this stimulation is also widely used in psychiatric disorders such as depression. So let's see some demonstration video. Okay. Yeah, maybe I don't use YouTube Premium, so okay. So this is Neuralink's first patient, Nolan, and in his brain, the Neuralink product is inserted. So he could control the cursor of the laptop only using his neural signals. Yeah, he can also stop the song and play the chess. Yeah, this looks fancy. And is it a new technology? Well, actually, no. The first neuro-recording IC paper that was published in 2003 in JAC by Harrison, and this is really a great paper. And also, currently, a lot of conventional neuro-recording circuits are still using this circuit, which was published like 20 years ago. And also, this full system that this tetraplegia patient controls these robotic arms to drink some bottle of water. This full system was published in Nature in 2012. Yeah, that's about 15 years ago. So actually, currently many companies, especially in US, are in commercialization phase and are working to obtain various FDA approvals, such as Precision, Synchron, Neuralinks. However, the technology they're trying to commercialize are not new, as I previously told you, and they're trying to commercialize the previous technologies and the systems to get the FDA approvals and to make the beer product to our money. This is a famous plot in neuroscience and neurointerface, similar to Moore's law. In the y-axis, you can see simultaneous recorded neurons. So 5, 10, 100, 1000, and this is the publication date. And when you see the trend, you can see that the number of simultaneous recorded channels are doubled in every 6.3 years. But as I told you, human brain has 100 billion billion neurons, which means we would require 200 years to reach the full scale of human brain. Therefore, we need some better tools to increase the number of recording channels more dramatically and make that 200 years to less than that. Now I would introduce about the circuits and systems for electrical neural recording. So these are brief classification of neural interfaces, which can be roughly divided into three categories. Recording only neural interface, which is recording human or animals' electrical neural signals with open loop neural prosthetics, and stimulation only to stimulate the target area. And also, there is a growing demand for this bidirectional neural interface, which both record and stimulate, which is largely used for closed-loop neural prosthetics and neurotherapeutics. We should first know about the characteristics of the neural signals. These neural signals can be divided into various signals, depends on where you attach your electrodes. The most famous one would be EEG, and there is also ECOG, which is called ECOG, and local field potential and action potential. And all those signals has really low frequency range. As you can see, it spans from 1 Hertz to 10 kilohertz. And also when you see the y-axis, the amplitude is also small. It spans from a few microvolts and to a few millivolt level, which means you have to design really low noise and low frequency circuits to detect and acquire these neural signals. And how do we sense these neural signals? We can just, how can we actually measure it? So there is a cell or neuron, and we attach electrode to interface with this cell and electrode. And this electrode conducts the electrical signals from these cells and transmit it to our circuit or system. And these systems amplify and quantize this analog signal to the digital output. And finally, we use digital signal processing to do some additional data analysis and feature extraction, and also use it with the AI algorithm. Yeah, in the last decades, we have seen a great improvement in this commercial neural recording system regarding this functionality, size, complexity, and price. As you can see, in 1980s, there was some equipment that could sense this physiological signals or biomedical signals, but we had to use this large equipment. And starting from 1990s, we started to use CMOS technology, which is one of the most advanced technology that humankind has, and made it really smaller. And also from 2010, it became really more smaller, in the size of this coin. And so high density multi-electrode arrays, MEA, has been developed, and also integrated circuit and signal processing has been developed. For the first part of this talk, I will briefly introduce about this recording only neural interface for open loop neuroprosthetics. And this is the conventional block diagram of neural recording circuits. It is composed of low noise amplifier, filter that you've learned in this course, and programmable gain amplifier, and analog to digital converter ADC that you will learn later in this course. First, let's think about how to design good low noise amplifier, LNA. How can you design good LNA? As a circuit designer, of course, we should know the specification for this neural amplifier. First, as I told you, the signal characteristics of this neural signal is as follows. Amplitude in a few microvolt level to maximum of like 5 millivolt. And frequency range is also important, and it spans from 1 Hz to 10 kilohertz. And about the typical specs for neural recording readout is input impedance is really important in order not to attenuate the signal. So our target would be over 100 mega ohm. And of course, one of the most important specs of this whole system would be noise and amplifier noise, which should be less than 10 microvolt RMS. And bandwidth should cover from 1 Hz to 10 kilohertz. Of course, CMLR would be important in order to reduce the power line interference and dynamic range. And of course, a really important one is power per channel. Because if there is too high power consumption, that could harm our body and tissue. Therefore, typically, we try to target this one below 10 microwatts. And of course, we have to make this chip and the system small. Area per channel is also important. Now let's do some theoretical things about this low noise amplifier. Maybe you may not be that familiar with this capacitive coupled neural amplifier, but you can just think this as same as just non-inverting amplifier with a resistance, which this one is just replace it to this capacitors. So there is Cin, CFB, and this resistor. We can think this as a resistor. And when you see here, the input impedance would be 1 over SC in, and DC input impedance would be infinite. So this topology is really suitable for this low noise amplifier. Also, the DC level of this input doesn't matter because DC is blocked in these input capacitors. Uh, Furthermore, because there is only capacitance, so there will be no noise contribution provided by this capacitor, not like just resistive inverting amplifier. And when you see the transfer function of V in to V out, we can see this transfer function, which is composed of this high pass current frequency, mid-band gain, and low pass current frequency. And this mid-band gain would be determined by, actually, I want to ask you guys, but I can see your face, so yeah, I will just go through it. So this
Sorry about that.
mid-band gain would be,
The camera
would
doesn't
be
work in my side.
Okay, okay. That's complete. Yeah, okay. So this mid-band gain would be determined by which one? Just, yeah, think for 5 seconds. Okay. It'll be determined by C in over CFB. Okay. Because if it is resistance, it'll be R1, R2 over R1, but this is capacitor. So it is just opposite. So CFB C in over CFB. Yeah, that would determine this mid-band gain. And do you know how this high pass cutoff frequency is determined? Yeah, 5 seconds.
Hold on a
Okay.
sec. Yoontae, hold on a sec. So
Yeah, yeah.
let me ask a question. So we have learned how to analyze this kind of amplifier plus something in Tau Thomas biquad and low pass filter, right? So you can simply apply nodal analysis at virtual ground node. Then you
Hmm.
can analyze this current flowing to C in is equal to CFB. So let's say this resistance is too high, so current doesn't go to resistance pass,
Yeah.
and all the current flows from in to out through C in and CFB. So you can solve this equation by just solving nodal analysis. Maybe I should think about having this one as a next quiz. Just kidding.
Yeah, yeah.
So please
Yeah.
go ahead, Yunte. Thank you.
Yeah, yeah. So, yeah, good explanation, Vante. So, yeah, by that way, this mid-band gain is determined. And when you think of this high pass curve frequency, how is this determined? Yeah, this is determined by this RC time constant between this CFB and this resistance. But as you can see, this high pass cutoff frequency should be placed under 1 Hertz, which means this RC time constant should be really large. If we assume this CFB as a few hundreds of femtofarad, and these resistance should be over 100 gigaohms to make this high pass cutoff frequency less than 1 Hertz. But actually, how can we implement 100 gigaohm in our integrity circuits? Yeah, we can't just put high poly resistance. And the chip would be full of the resistance. Yeah, so at the paper that I told you, he has some good idea, which is pseudo resistor. Now, pseudo resistor means it is just works like pseudo resistor by only using these two transistors in diode connection. The theory is pretty simple. So you use this transistor as diode connected most biased in this cutoff region. So there will be really small current flowing through these transistors, which is less than femtoampere level, and which means that we can see this as something like pseudo resistance. And we can get equivalent resistance values over 100 gigaohm by only using this two transistor, which is really area efficient. However, of course, as you can see here, it can be very nonlinear, and also there's been a lot of works to linearize and make these pseudo resistors more robust. But first, this pseudo resistor is one of the important components of this neuro-recording circuit, so it's better to keep in mind. So next one is noise. I think some of you guys have already learned and studied about this amplifier and about the noise, how to analyze this amplifier noise. And we don't really use this 5-tier OTA in Neuro-recording, but just for simplification, I brought this one. And do you know this 5-tier OTA, right? So the input is amplified, and output you have open loop gain of GM R out. And when you analyze the thermal noise of this amplifier, you can get this kind of equation, and that's pretty straightforward. There is GM of input here and GM of this active load here. Then how can we decrease the thermal noise of this low noise amplifier? Yeah, we should decrease this one. We should increase, we should increase this one, the input transistors GM, transconductance, and we should decrease transconductance of this active load GMMB. So design guidelines will be pretty straightforward for the simple 5-tier OTA. And also it applies to many amplifiers such as two-stage amplifier or current reuse amplifier. So yeah, one thing, you can of course analyze this kind of noise analysis, but actually for analog circuit designer, you have to have some intuition. So please keep in mind this design guidelines. Input transistor should maximize GM, this one. And also, in this field, in order to maximize GM more, we put these transistors in weak inversion, which can really increase the GM over ID to over 20 and 30. So if it's possible, in this application, we're trying to put this input transistor in weak inversion. And when you see this active loads, many of students are kind of confused with this one, but you should keep in mind, it's better to set this GM of this active loads lower. So minimize GM and make it in strong inversion. So that's kind of the basic design guidelines for this low noise amplifier. So other than that, we have some several techniques in order to get rid of 1/F. But Gante, the students have learned about the noise in this course? Not yet?
In basic source design, we have studied, right? What
Okay,
is
okay.
about thermal noise, what is about flicker noise, which is 1/F,
Okay, okay.
right?
Then it'll be perfect. Yeah. As I told you, the signal, our desired signal frequency spans from 1 Hertz to 10 kilohertz. So when you see 1 Hertz, what would be important? Yeah, of course, 1/F noise would be really critical. Therefore, there has been a lot of researches how to reduce this 1/F noise. The most straightforward thing would be just just increase the size of this input transistors and this biotransistor. If you increase the size of these transistors, 1/F noise will be also reduced. However, we can just make it larger because there is some saturation and the chip will be full of the input transistor. Therefore, there has been some techniques called chopper modulation, which is to modulate the signals. So there is modulator and demodulator here. And if you think signal spans from here, after this modulator, this signal is modulated to chopping and with the harmonics. And we go through this IA in this region, and offset and noise is in this lower frequency. In the end, this one, with this signal, offset and 1/F noise will be added like here. And after it is amplified, when we demodulate this final output of the amplifier, signal goes to the baseband, right? And this offset and 1/F noise is modulated to chopping frequency. Therefore, this frequency range becomes different between the signals and low frequency interferences. And if we filter out this one, we can get rid of this offset and 1/F noise. So advantage of this chopper amplifier is it's pretty simple. Actually, we can just implement this one with simple 4 switches, and we can get rid of 1/F noise and mismatches. However, there is no free lunch. Disadvantages are reduced input impedance because this is shuffling every time impedance is reduced. And of course, following IA bandwidth should be enhanced like 5 to 10 times of chopping frequency, and also there will be some input spikes and chopper clock feed through. And finally, it's pretty difficult to implement this one in multi-channel neural amplifier. Yeah, we look through the LNA and let's go through to this ADC, analog to digital converter. There wasn't FOM, which is the figure of merit in this ADC field. So you can think this as the power efficiency. So lower, the better. And this plot is Boris Merman's ADC plot, that is showing ICC works between 1997 and 2020. And you can also see the latest version when you go to his GitHub. And when we think about our application doesn't need to. So for the x-axis, it's we can think this as a sampling frequency. So for our application, we don't need this high frequency, high sampling frequency. So we should target in this range under 1 MHz. And when you can see when you see this slide here, these sections shows good FOM margin. And when you see this structure, you can see this as a star ADC. And also there's another metric called Schreier FOM, which concentrates more on the resolution of the ADC. And also in our target, we can select something in this one. So in this Schreier FOM, higher the better. So also star ADC would be good candidate. And also this purple one. Yeah, delta sigma ADC can be another good candidate. Therefore, in this field, popular AD topologies are star ADC and delta sigma ADC. And you are going to cover this star ADC at the end of this semester in this course, and you will learn the detail about it. Okay, we learned about one-channel neuro-recording. Then how can you scale this to multi-channel circuits? Can you just make it all thing in parallel? Like putting 1, 1, 1, 1, 1. But you should keep in mind that we are targeting 1,000 channel neuro-recording and over than that, like 10,000. We can't just put this one because the chip size would be too large. So many people are doing this multiplexing to reduce the circuit area and circuit block that we have to design. So in many cases, we multiplex this amplifier output to the ADC using 16 to 1 mux or 8 to 1 mux. And also, one thing that we have to keep in mind is this electrode array. How can it connect this electrode with our active circuit? Can you just connect it with fixed wiring and connect everything with wires? Actually, there are some methods how to connect these electrode arrays with our circuits. First one is, as I told you, straightforward fixed wiring to connect this electrode to our active circuits one by one. And the second one is static selections to use additional mux in front of these our circuits to select which electrode to be connected with our circuits. And the last one would be scanning to sequentially record all the electrode arrays. So first, let's look through fixed wiring. This is the electrode and this is our active circuit. And when we are using this fixed wiring, it's pretty straightforward. But the problem is routing congestion here limits the number of recording sites and simultaneous recording channels will be also reduced. Second method would be static electrode selection, that we can select which electrode to be connected with our amplifier. And the good thing is we can use only one memory and one switch in each pixel, and it becomes high density. And this neural amplifier here is not constrained by pixel size, and we can invest a little bit more areas to this high performance amplifier. The bad part is because we can just statically select it, there is limitation in simultaneous readouts. And also one thing to keep in mind is for some systems and for circuits, we put this pixel amplifier right next to electrode array. So this is called as active pixel, which is widely used in this biomedical field. An amplifier is placed right below each electrode. And actually it buffers this electrode to this amplifier. Because as you could see here at the first slide, the routing from this electrode to our active circuits can be really long, about a few millimeter. And also, this line is really tiny, which means there is a high output impedance of this electrode. Therefore, in many cases, we put this active pixel to buffer and reduce output impedance of this electrode array and also reduce crosstalk. The last method would be dynamic array scanning, which is to scan this electrode sequentially with fast scan. So 1, 2, 3, 4, 5, 6, and go again and 1, 2, 3, 4, 5, 6. So it's basically full frame readout and time domain multiplexing. However, we need a pretty good this pixel amplifier to drive these electrodes. And this pixel amplifier can be sized and the power consumption can be enlarged. So this is a brief section summary. For the fixed wiring, it is smallest recording electrode and smallest simultaneous channels. And the static selection and dynamic scanning has large recording electrode. And this dynamic scanning has largest simultaneous channels with trade-off in the power consumption and area consumption. So first, let's see some works that implemented over 1,000 channels. And this is Neuralink's N1 ASIC, which use 1,024 channels. And now we can easily see, we can easily analyze the circuits, right? Because it's pretty straightforward and they only have the components that I already explained. Yeah. It is capacitively coupled. This LNA, bandpass filter, VGA is PGA, and there is multiplexing 16 to 1, and this ADC. So this one module gets 16 channels, and there is 16 more of this one, and of course there are four tiles of this one. In the end, this chip could record 1,024 channels using static selection of the switching matrix. When you see this performance matrix, it has imperial noise characteristic of 9 microvolt RMS, power of 24 microwatt, and area per channel would be 0.02 square millimeter. So let's see some highlights from imec. In imec, we're concentrating on high density neuro-recording circuits. The most recent one had 5,120 electrodes with 1,536 simultaneous recording channels. And these are some portfolios that we have so far from the NeurPixel projects. And we have been developing really well in terms of the circuits. And also, we are making these really small systems and PCB to merge the circuits to the real product. This is NeurPixel 1.0 with active CMOS NeuroPro. This is monolithic silicon NeuroPro with 966 electrical recording sites, and this is the circuit to obtain the signals from this active electrode with 384 concurrent low power, low noise recording channels. One thing special in imec is, as I told you, we have fab. So we could make these electrodes and do the post-processing by using this imec's unique fabrication utility. We all implemented this electrode and chip in CMOS wafer, and after that, we had to do some etching and make it thinner and also put titanium nitride electrode on it, like this one. And that post-processing was done by also imec. So let me briefly introduce about this circuit of this Neuro-recording 1.0. That's all we learned. We have static selection and there is pixel amplifier in every electrode with amplifier, switch, and memory. And it is followed by capacitively coupled IA, and there is bandpass filter, high pass filter, and low pass filter, followed by programmable gain amplifier, additional MUX, and 10-bit RADC. With this topology, we could achieve simultaneous recording of 384 channels with input noise characteristic of 6.4 microvolt RMS, and power is a little bit larger because it sums all the auxiliary circuits, not only the circuit, but all LDOs, BGRs, and digital circuits. So it seems a little bit large. And total area is 0.12 millimeter square. So this is a post-CMOS fabrication process. And we have this CMOS wafer ready. And only for that electrode part, we are trying to deposit this electrode. This is titanium nitride electrode because this electrode should be biocompatible. This should be okay even when you insert it into human body or animal body. Therefore, we are doing etching, frontside etching, backside etching, and finally dicing to make them thinner. And we were able to make this electrode with this titanium nitride electrode deposition. And second one was NeuroPixel 2.0, which targets to optimize the area consumption. Therefore, we got rid of some high-pass filters and additional programmable gain amplifier and the active pixels. Therefore, the circuits became pretty simplified and we could reduce a large area. And also, in order to increase this electrodes, we use quad shank structure. And also, as I told you, in this every pixel amplifier was removed thanks to the enhanced technique of this electrode. Finally, we got 5,000 electrode, 384 number of channels simultaneous recording, input preferred noise of 7.4 microvolt RMS, and total area of 0.05 square millimeter. And these are the device details of this quad shank. Yeah, as it is the pitch of the electrode has been reduced, and also it became more thinner compared to NeuroPixel 1.0. And this is NeuroPixel 3.0 NXT, which is composed of 5,000 electrodes and 1,536 channels. And the circuit has been well optimized, and and higher process were used, and it reduced 10 times area consumption. As you can see here, 0.012 square millimeter with low power consumption of 19.3 microwatt, and also input noise has been reduced a lot. And also in this product, quad shank was used to reduce, and this base size was also reduced, and the final product was implemented using this circuit. Now, this is the NeuroPixel portfolio, and to cover several animal models from small rodents to non-human primate models, we are actively working on collaborative project with a wide range of companies, startups, and research institutes. Now, this is NeuroPixel 1.0, NeuroPixel 2.0, and this is NHP. And as you can see here, compared to the Euro, this chip is really small. Okay, so I wanted to cover a little bit about the bidirectional neural interface, but we're a little bit lack of time, so I will go really briefly with this bidirectional neural interface. Nowadays, there are growing demands for this closed loop neuromodulation, not only recording it, but also stimulating it with respect to the incoming neural signals. So when there is epilepsy or some stroke coming, you detect it by recording circuits, and right at the moment, you stimulate the target area with electrical stimulation. And some of the research proved that this closed loop modulation has higher clinical efficacy. And there are some products from Europace and Medtronic targeting this closer neuromodulation. And the block diagram is like this one, recording and stimulating. And if you want to design the neural recording circuit for this bidirectional neural interface, there is one more obstacle. Because as you can see here, there is stimulation circuit, and the stimulation artifact would be transferred through the cells and get into the neural recording circuit. Therefore, there would be large stimulation artifacts. Therefore, the final requirement for this circuit would be not only low in peripheral noise, but also a wide dynamic range. Because you can't just filter it out, because the frequency range of this stimulation artifact and motion artifact are more or less the same in this our desired signal. So you can't just put a bandpass filter here. Therefore, nowadays, many people are trying to get all the information of neural signals and the stimulation artifact and cancel it and deduct it at the digital backside. Therefore, for this bidirectional neural interface, dynamic range has been one of the most important performance metric. Yeah, when we use just conventional amplifier with ADC, if there is this abrupt artifact, this can go through this capacitor. Therefore, this amplifier's output will be saturated. And as I told you, this artistic time constant is really large, and it will take several seconds to make the circuit work properly again. Then how can you increase this dynamic range? Yeah, what should it change in this circuit? The answer is pretty straightforward. Just get rid of this amplifier. Just put the ADC. But of course, there is no free lunch. If you just put this ADC, this ADC's noise performance should be lower than the 10 microvolt RMS, which is pretty hard when you learn about this ADC in the later of this course. Therefore, some state-of-the-art direct digitization recording ICs concentrated this one and implemented the structure using high-order delta sigma ADC, achieving more than 89 dB SNDR performance. So this is a third-order continuous time delta sigma ADC, but this consumed a little bit more power consumption, and there has been some approaches to reduce the power consumption and maintaining the SNDR performance using this time-based ADC using VCO or CCO in the circuit. And also there has been some works targeting high dynamic topologies while maintaining moderate SNDR performance by putting some integrator in the feedback and using a lot of works. And for the multi-channel implementation, incremental delta sigma ADC has been also implemented. To wrap up, amplifier plus ADC and direct digitization works. There are some pros and cons. This amplifier plus ADC conventional work shows good power, noise, performance, but limited dynamic range performance. However, this direct conversion topologies has bad power and noise performance. However, it's good for dynamic range performance. Also, in imec, we are also designing direct digitization ASIC, which is composed of a delta delta sigma architecture. So it's a little bit complicated, but you add this additional integrator or accumulator in this feedback path, and you could implement this delta sigma architecture, and this work could shape the signal transfer function to high-pass filter and enlarge the dynamic range pretty well. And the good thing about this direct digitization is we don't need amplifier or other circuits. Therefore, this channel area will be greatly reduced. And also, there has been some works, and we reduce area per channel dramatically. Therefore, the target of most of this neuro-recording field is to make more channels and make each channel more smaller. And of course, when you can see here in the readout channel of imec's portfolio, NeuroPixel 1.0 was this large, 2.0 became smaller, and using this direct digitization, it became really smaller, about 16 times area scaling. This is a comparison of each architecture, and IA plus ADC shows good power performance and good noise performance, but larger area. And this direct to digital architecture shows good area efficiency. Okay, we're in almost yeah, final slide, so I will wrap up this one in like 1 minute. So what is left? Actually, now there is also neuro-recording data bottleneck. When we assume resolution of 10 bit, 30 kilo sample per second, and number of channels 100, you need 300 megabps with really small power consumption, which is really hard. And this transmitting low data over wireless is power hungry, and that can be over than the channel's power consumption. And uh, in order to mitigate this one, we're also developing on-chip signal processing with data reduction and feature extraction and spike sorting. But the algorithm can be easily computationally intensive, so we have to balance it really well because of the trade-off between transmission power and processing power. So we are also approaching spike sorting and a lot of digital algorithm to do some on-chip processing. And spike sorting is kind of really identify spike times of individual neurons and which neurons are firing. And it can obviously reduce the data rate significantly. But one question is, how can you do this efficiently for 1,000 channels on chips? And this research is still ongoing in this field. And this is a conclusion. So as I told you, we have done incredible progress in this new recording field, but yet still we have long way to go. First one is high density analog. As I told you, our target is to achieve more than 100K simultaneous recording. And of course, material science for the electrolytes are also important. Wireless power and data transfer is also important, and digital signal processing, spike sorting. And the last one would be compressive sensing and how to compress all these signals in analog or digital way. So this was my talk. So thank you for listening.
Thank you. Thank you. Thank you
Thank
very
you.
much for a very nice talk. So, do you have any questions before we conclude today's lecture? You can also post the question and press them. I can deliver that question to Yoontae.
Yeah.
Yeah, very nice. Okay, thank you, Yoontae. So, yeah, I will catch up with you later. So,
Okay, sure.
we will conclude today's lecture by this point, and we will move to quiz. Let's take a break, probably like 3 minutes. Thank you, Yoontae.
Okay, thank you.
Thank you.